In this video, I'm going to talk about fast exponentiation. This is more of a computer science topic than a mathematics topic. What we're going to do is we are going to come up with an algorithm to compute powers of numbers faster using no new mathematics. So it's just a trick. We are just going to exponentiate, but we are going to do it smart. Okay, so that's what we're going to do. And the setup is the following. Suppose we have two positive integers m and n, and I want to write a program that computes m to the k mod n for different values of k. Okay, so m and n are fixed. So the thing that I'm taking the power of and then the thing that I'm taking the remainder to are fixed, but I'm repeatedly asking for different powers of m. And this is needed, for example, in the RSA algorithm that we're going to see in a couple of videos. So let's take examples. Let's say m is 5 and n is 23. And then my goal is to compute repeatedly 5 to the k mod 23. So now the simplest algorithm, but the slowest, is to just do it by hand. Right, just use the definition and multiply 5 to itself k number of times. This is also the slowest method. And why is this slow as far as like in the long term? Because let's say I have a query. Suppose I ask what is 5 to the 100, and you give me an answer. And next I ask what is 5 to the 101. Well, then if I use this algorithm, then I'll just have to do 5 times 5 times 101 times. But a smarter thing to do would have been, I remember that the answer for 5 to the 100, whatever it was, and then I multiplied that with 5. And so the key is that instead of having to compute this a power of 5 every time starting from scratch, I remember some powers of 2. So the fastest method, but which is not very practical, is to store all values. So let's say I know that my inputs are always going to be less than or equal to 1000. So I just store all 5 to the 1, 5 to the 2, 5 to the 3, 5 to the 4, 5 to the 5, and so on, all the way up to 1000. Of course, this takes a lot of memory, but at least, but it's really fast, because then when I get a query, I just look up in the memory and output the answer. It's not very practical to store such a long, store so many numbers in the memory. So now we're going to look at a method that is in between these two things. So it's slightly smarter than the simplest method, but it's takes less memory. So we will remember some powers of 5 and not all. And from those few powers of 5, then we'll compute the rest of them. And so we will use the binary representation method. And what this method says is you remember 5 to the 2 to the k for some values of k. Okay, so I remember the powers of 5, but the powers are now only powers of, the powers themselves are powers of 2. I'll remember 5 to the 1, which is 5. Then 5 square is, I'll remember 5 square, which is 25. Then I'll remember 5 to the 4, 5 to the 8, 5 to the 16, 5 to the 32, and so on. So I'm not remembering anything between 5 to the 4 and 5 to the 8. Nothing between 8 and 16, 16 and 32, 32 and 64. Okay, so I'm remembering a few things, and these are very few. Like, no matter how big the powers can go, because I'm only remembering powers of 2, that's hardly anything. Like, this is log many number of things I'm remembering, and log of n is a very slow function. So this is ideal. I'm remembering only log many terms. But now the question is, if I just remember these, then how do I recover, how do I compute powers of 5 when the power is not a power of 2? And for any other query, use binary representation. So let's do a concrete example. Suppose I am asked to compute 5 to the 17 mod 23. So I'm going to write an algorithm which is 2 steps. First is pre-processing. The pre-processing step is I store in my memory 5 to the 2 to the k for various k. 5 to the 2 to the k mod 23. And how do I do that? Here is another trick that I'm going to use that will make this process very fast. Notice that 5 to the 2 to the k plus 1 is nothing but 5 to the 2 to the k times 2, which is nothing but 5 to the 2 to the k whole squared. So 5 to the 2 to the k plus 1 is 5 to the 2 to the k whole squared. So if I know what 5 to the 2 to the k is, then the next step is obtained by simply squaring that thing. Then the next step is obtained by simply squaring that thing, and so on. And here's how it goes. 5 to the 2 to the 0 is 5 to the 1, which is just 5 mod 23. Then 5 to the 2 to the 1 is obtained by squaring the previous thing, which is 25 mod 23. Now 25, when you divide by 23, gives you remainder 2. Then 5 to the 2 square is square the previous thing, mod 23. And that gives me 4 mod 23. And then 5 to the 2 to the 3 will be 4 square mod 23, that is 16 mod 23. And now 5 to the 2 to the 4 will be 16 square mod 23. 16 square is 256 mod 23. And let's do a long division to figure out what this is going to be. This will be 3 mod 23. So what I've computed is I've shown that the first power of 5 is 5 mod 23. Then I've stored in my memory that the second power of 5 is 2 mod 23. Then the third power of 5, then the fourth power of 5 is 4 mod 23. Then the eighth power of 5 is 16 mod 23. And finally, the 16th power of 5 is 3 mod 5 to the 2 to the 0, 5 to the 2 to the 1, 5, then 2, then 4, then 16, and then 3. Okay, so that's the pre-processing step. And now I'll do the computation, which is compute 5 to the 17 mod 23. So now what I'll do is I'll take 17 and I'll break it. I'll find its binary representation. I find 17 mod 2, and then I'll find 17 div 2. 17 mod 2 is 1, 17 div 2 is 8. Then I'll do it again. Then I'll do this again. And I'll get 0 and 4. Then I'll do this again. This again. I'll get 0 and 2. And then I'll do this again. Again, and I'll get 1 and 0. Okay, and once I reach 1 and 0, I stop. So that is my binary representation of 17. So 17 in base 10 is 1 0 0 0 1 in binary. I can expand this as I'll start from the right hand side. 1 times 2 to the 0 plus 0 times 2 to the 1 plus 0 times 2 to the 2 plus, so right now I am on the second 0, then the third 0 is 0 times 2 to the 3, and then I'm in the fourth one, 1 times 2 to the 4. Okay, so that's the binary representation of 17, and when expressed in powers of 2, this is what I get. Just so that we are clear about where the numbers are coming from. This one is this one, this one is this one, and the rest of the zeros are the 3 zeros in the middle. I'll discard the zeros for the sake of simplicity, and I'll get 17 is 2 to the 4 plus 2 to the 0, which you can see it's true. 17 is 16 plus 1. The reason for doing this is now I can use my pre-processed powers of 2 to compute 5 to the 17. So 5 to the 17 mod 23 is 5 to the 2 to the 4 plus 2 to the 0 mod 23. I'm just writing 17 as 2 to the 4 plus 2 to the 0, which is then 5 to the 2 to the 4 times 5 to the 2 to the 0. And here I'm going to use the table. I know what 5 to the 2 to the 4 mod 23 is. That number is exactly 3. And I know exactly what 5 to the 2 to the 0 mod 23 is. That number is 5. And so I'll get this is 3 times 5 mod 23, which is then 15 mod 23, and 15 is less than 23, so the remainder is still 15. And so my conclusion is that 5 to the 17 is 15 mod 23. Notice that I did not need any calculator to compute the 17th power of 5, which is incredible. So that's fast exponentiation. Even though it took a while to reach this number, it's nothing compared to having to compute multiply 5 to itself 17 times. Final remark, let me just say that there is nothing special about mod n. This can also be used. Can be used just to compute powers. You don't need to have mod n. Of course, the numbers would be bigger because you're not taking remainders modulo or anything, but that's still fine. If you're using a computer, it can save large numbers. And this is still much faster than having to multiply things out by hand.